Yes.
Hello, everyone.
Hello.
Welcome back to the Deep Tech podcast. This is the third episode.
Is it? I think it's the
No,
fourth.
it's the fourth
Yes,
episode.
yes, yes.
Yeah. So, Deep Tech podcast. And as promised, this time we're going to focus on lithium ion batteries on the second iteration. A bit deeper in the science. And specifically, I want to discuss today, I want us to look at it from the first principle point of view,
Mm-hmm.
which means that like the simplest way possible,
Mm-hmm.
and looking at it from that point of view, and then specifically going to the battery degradation processes, and specifically on the lithium cobalt oxide batteries, which is the fanciest batteries, like the
Mm-hmm.
highest density
Mm-hmm.
that is commercially available.
Mm-hmm.
And this allows us also go to a bit of a connected to our day-to-day life,
Mm-hmm.
the instrumentation market, um, what do you call it, analytical instruments and measurement devices and techniques and materials.
Mm-hmm.
Yeah.
Why we wanted to do this? Just a bit of context. So we were discussing in the last episode. We talked about how batteries work and all the new battery chemistries coming in. It was very scientific, but we wanted to talk about a bit more about what is needed from batteries in the next years. That's why we focused on, for example, battery degradation, and we wanted to talk about what is contributing to improving the performance of
Yeah.
batteries. Both from the technical perspective of how batteries work, but also from the wider perspective of what technologies and instruments are needed to make this happen, and how the market around it works.
The funny thing is that if you look at it from a point of view of first principle, they call it in Latin in situ,
In situ, yeah, kind of. Is
right?
it? Yeah.
No,
No, in situ
no,
is
no. In
in
situ is by
place.
time.
In situ is in
Ab
place.
initio.
Yes, yes,
Ab initio.
that's right.
Right.
Ab
Sorry.
initio. Yes,
Ab
yes.
initio. In situ means so means so it becomes very clear why and certain techniques that is needed and why what needs to be done and such, which is very cool. Which is very cool.
Let's see. Let's start with this. This is a
Yeah.
plan. We'll see where we go.
Yeah.
Let's just jump into it.
So how does lithium ion batteries work?
Mm-hmm.
Specifically lithium cobalt oxides.
Mm-hmm.
Let's make a very simple mental model. Let's think of lithium ions like marbles, little marbles, and then let's look at the uh, battery, the difference or the voltage or electrochemical differences
Mm-hmm.
as like a ramp,
Mm-hmm. Mm-hmm.
right?
Mm-hmm.
So when we're charging batteries, the marbles are at their rest state where it's in the cathode.
Yeah, they are at the bottom of the ramp,
Yes,
and
they
when we
are.
are charging, we are pushing them up the ramp.
Yes,
Yeah.
and the ramp is the build of the material, and the how steep the ramp
Mm-hmm.
is based on the electrochemistry and physics and the materials used in the battery,
Mm-hmm.
in the anode, cathode, and also the structures.
Mm-hmm. Mm-hmm.
So let's think of it like that. So I want to think of it like that and like see how far we can push that
We can keep
analogy.
referring to that. So the cathode would be the bottom of the ramp.
Yes.
The anode would be the top of the ramp.
Yeah.
And the ramp itself would be the electrolyzer.
Electrolyte.
Electrolyte. Yes, that's right. Yeah.
Yes. So when we are charging, and then think of it like, if I want to make it simple, the anode is mostly graphite,
Mm-hmm.
and the cathode, which is the bottom of the things, is um, layers of uh, cobalt oxide that between it is looser. Lithium ions are looser, but it's very bonded to it, but it can be removed. So essentially, think of it as shelves,
Mm-hmm.
right? There are some shelves on the top of the ramp, there are some shelves on the bottom of the ramp.
Mm-hmm. Mm-hmm.
So why we are not using graphite both sides? Like, think of it like the marble goes up, it goes in between these layers
Mm-hmm.
or stack of papers, let's say,
Yeah.
between them,
Yeah.
and there are a stack of paper bottom.
Mm-hmm.
And kind of they're similar that they are layered structure, both of them,
Mm-hmm.
right? But one, the lithium likes it more to be there, which is the bottom of the ramp,
Mm-hmm.
which is between the layers of cobalt and oxygen.
Mm-hmm. Mm-hmm.
And you need to give it energy to remove it from there,
Mm-hmm.
push it on the ramp, and put it on the other shelf.
And then in the other shelf, it is kind of stable. So
Yes.
you need a bit of energy to push it back down, but then it goes naturally. It's attracted to the other side, no?
Yes. Um, yes. It is not, it will go back,
Mm-hmm.
but the thing is that, like, because we don't let the electrons. So when we are moving it from the bottom of the shelf,
Yeah.
right, like the bottom, there is an extra electron
Mm-hmm.
that stays on the cathode.
Well, no, the extra electron goes around.
Yes, but
Yeah.
the extra electron stays here,
Mm-hmm. Mm-hmm.
and it goes there, and electron goes from the other side, and they reunite,
Mm-hmm.
right?
Mm-hmm.
But if you let it, because the electron cannot travel from the electrolyte,
Mm-hmm.
right?
Mm-hmm.
It doesn't come down.
Mm-hmm.
It needs to leave the electron down, but the electron attracts it back because it's positive, and the negative, it doesn't let it roll down the.
It's already so hard to fit it into the analogy. Yeah.
Yeah.
Yeah. So the marble, the lithium, and the electron want to be together. The lithium is positive, the electron is negative, the lithium ion is positive. So when charging, they are at the bottom of the ramp. The lithium comes out of the cathode, uh, and the electron also goes out of the cathode, but the electron goes through the wire, and the marble goes up the ramp.
Yes.
And then they meet together at the top of the ramp. And then when you use the battery, again, you connect the circuit at the top, so the electron wants to go out, which means that the lithium also wants to go out of the graphite, and it goes down the ramp, and they meet at the cathode
Yes.
again. It's it's
So there
tricky.
is, like, this analogy helps me understand
Mm-hmm.
some basics of why electrodes, like why the capacity or charge or aging
Mm-hmm. Mm-hmm.
goes can be affected.
Mm-hmm.
So the density is affected by how steep the ramp is or how high the ramp is
The density,
of
but
energy.
isn't it also how many gaps there are in the?
Yes, but that is the charge density, but also the voltage. So
Mm-hmm.
the voltage is how steep the ramp is.
Right. If the ramp is steeper, the marbles go down with more
Faster,
force. Yeah.
and there is no more energy stored. So because you need to do more work to
Right.
push
So
it up.
for each marble
Yeah.
stores more energy if the ramp is steeper, and the
Yes.
other way is to have more marbles.
Yes.
So you to have more slots for
Yeah.
marbles in both sides.
Yes.
Hmm.
Then there is, if the marbles can um, freely flow on the ramp.
Yeah.
If there is anything preventing them,
How smooth the ramp is, or
yes, or
yes,
if there is something, like, essentially, if you have a net that they need to go through that net.
because you do need to kind of have a net so that the electrons don't go
Yes,
through.
exactly.
Yeah.
Because the electrolyte is just a solution, electrolytes, right? They are ions inside it.
Hmm. Hmm.
If you were a kid, you would put two electrodes in salt water.
Hmm.
You would start seeing, like, hydrogen and oxygen bubbling from two sides,
Hmm.
which means that there is electron moving.
Hmm.
Also, is conductive,
Hmm.
right? If you, like, I don't know if you have ever, they said, like, never, like, people dropping the hair dryer in the
Yes,
in the
yes. In the
bathtub,
bathtub. Yes, yes,
right?
yes. The toaster. Yeah, yeah.
Those stir and
Yeah,
such,
yeah.
because it's conductive.
Yeah, yeah, yeah.
So if so the electrolyte not only can push ions, but
Mhm.
also can conduct electrons in
Mhm.
principle.
Mhm.
So we
Mhm.
need to avoid that.
Mhm.
That comes later,
Okay, okay.
right?
Okay, so electrolytes are conductive in
Yes,
general.
because they are full of salt,
Okay, so you need a barrier in the middle. Yeah, okay, okay.
and the barrier is for not them let them touching,
Mhm.
but there is another barrier that comes, which is called, um, let me see, solid. I forgot. I'm very bad with. So solid electrolyte interface.
Yes, okay. Yes, that makes sense. So again, to recap, it's not just the ramp and the marbles. The ramp actually has a net in the middle so that electron don't pass through.
Yes.
So you let the marbles, the lithium ions down, but not the electrons.
Yes. Now the question comes: why cobalt?
So cobalt is in the cathode.
Yeah, in the
So
bottom round.
you were saying that in the bottom ramp, that material, yeah, it tends to be a bunch of layers of metals, oxygen, and in the middle you have the lithium.
Yeah.
Yeah.
So it gets removed,
Mm-hmm.
but then when there are two states, then metal like cobalt oxide without lithium
Mm-hmm.
and cobalt oxide with the lithium.
Mm-hmm.
In these two states, it's stable,
Mm-hmm. Mm-hmm.
right?
Yeah.
And the other thing is that the difference of energy of these two states, so it's stable and reversible,
Mm-hmm.
right? So you can both put the marble, take it and put it back. You remember, like as a kid, I hated that I needed to buy new batteries because it was not reversible.
Yes. Yes. They're rechargeable. Yeah. Of
Yeah.
course. Yes. Yes. So okay, and the way you trigger this is by adding and removing an electron.
Yes. So you put it in an electric field, essentially, when you're charging it.
Yeah.
Then the electron wants to, because when lithium is three, it has three electrons,
Yeah.
one more than helium.
Mm-hmm. Mm-hmm.
So the more it's that electron is quite loosely connected to lithium.
Mm-hmm.
So when it goes to oxygen, which is very hungry
Mm-hmm.
about electrons,
Yeah.
the center of mass of electron,
Yeah.
and the ion, or like the nuclei
Mm-hmm.
of, is quite separated.
Mm-hmm.
It's
Mm-hmm.
closer to oxygen.
Mm-hmm. Mm-hmm.
So when you put it in an electric field,
Mm-hmm.
you the ion wants to go to the negative
Mm-hmm.
side
Mm-hmm.
of the electric field,
Mm-hmm.
wants to go through the electric field,
Mm-hmm.
and the electron wants to go to the positive pole,
Mm-hmm. Mm-hmm.
right?
Mm-hmm. Mm-hmm.
Which means that it gets separated,
Mm-hmm.
right? There is another thing that it's makes it very, very good,
Mm-hmm.
that different there is a big difference in energy, electrochemical energy, or the ramp is quite steep
Mm-hmm.
for cobalt oxide and with electron, and without with lithium and without lithium. The energy difference of these two states of material
Mm-hmm.
is quite high. It's
So
reversible, but it's high.
so yeah, okay. So when you snap out the lithium from it,
Yeah,
so it takes quite a lot of energy to take the lithium out, and it takes,
it gives a lot of energy back
yes,
when,
it gives a lot of energy back if you put the lithium in.
but still stable.
Yeah, it's still stable. Yeah,
So
yeah,
it's a very, like, normally if you really need to put a lot of energy into it,
yeah.
you destroy the structure of the material.
Mm-hmm. Mm-hmm.
But here you give a lot of energy and remove the the lithium, but still the remainder stays intact.
Mm-hmm. 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 And cobalt has this property. So if you use other metals, you just have a different amount of energy differential between the two states. Is that the main difference?
And also the
Because it's quite common to use like manganese or
yeah, the
other
thing is
similar.
that it's very cool.
Mm-hmm.
I mean, this was part that I hated a lot, and I had a professor that it was very hard for on us. Like in solid state, when you study, these are like these atoms, they would pack differently in a material
Mm-hmm.
depending on difference of their sizes and how they bond to each other. So
Mm-hmm.
if you um, change cobalt to manganese or like magnesium or something,
Yeah, manganese.
then you are gonna change the structure of the solid as well, the
Yeah, the
lattice.
structure of the crystal. Yeah.
Yes,
Mm-hmm.
which means that then it changes, it behaves differently when you remove. So it's not layer anymore.
Okay, okay. So
So it's
it
a three dimension.
rearranges
Yes.
differently. Okay.
So which is more complex than you can think of.
Right.
How it's not simple like just let's move this and like put another one.
Mm-hmm.
The packing structure, how they pack to each other,
Mm-hmm.
is gonna be different.
Yeah, it's a different amount of lithium that can fit in and
Yeah.
a different amount of energy it takes to take it out.
And also how stuck it is in the
Yeah.
structure, how permeable, like what do you call it?
Permeable.
Permeable
Yeah.
it is to lithium.
Mm-hmm. Mm-hmm. And I guess the surface area also has an effect
Yes.
if there's enough, yeah, surface area for the lithium to come in and out. Okay. Um, we started uh, saying that we wanted to talk about um how batteries. So when you repeat this cycle,
Yeah.
uh, why does it become less and less efficient? We all know how when we use our phone for a couple of years or any electronics for a couple of years, it keeps lasting less and less.
Ah, yeah.
So what happens in the
That's
battery?
annoying, like that my iPhone doesn't last after 2 years
Yes, yes,
anymore as much. And
yes.
imagine if you have a car
Yeah.
that most of the value of the car is the battery
I'm
or
not
the
sure
chunk.
how much of this is on purpose. Sometimes it's a bit suspicious. I got these amazing headphones. At the beginning, they would last for like 9 hours in a single charge, and after 2 3 years, it would be like less than 30 minutes on a single charge, and it was a gradual
But I
change.
think it's also may change, like you might make sense how
Mm-hmm,
it is,
mm-hmm,
like
mm-hmm,
So you remember I said this solid electrolyte interface,
mm-hmm.
right? So the thing is,
So the net in the middle of the ramp.
yes,
Yes.
you know what happens? This electrolyte is in contact with the graphite,
Okay. Yes. Yes. Yes.
right?
Yeah.
And these are a lot of polymers and radicals and like also salts
Okay. Mm-hmm,
in the electrolyte.
mm-hmm,
When you put it the first time that you charge it,
mm-hmm.
it reacts on the surface of the anode on the graphite.
Okay. So besides attracting lithium, it attracts some stuff from the electrolyte,
Yes, and then
and they
react on the surface.
so they get stuck. It's like
Yeah,
a
they make
crust.
a essentially make a crust on top,
Yeah. Okay.
right?
Yeah. Yeah. Yeah.
That is positive.
Mm-hmm.
That makes let's electrons do not it is not conductive, this layer.
Okay.
So the electrolyte is not in contact anymore with anode.
Okay. So there's an electric field which is attracting the lithium, but it's not conductive. So the
Yeah.
okay, the electrons cannot pass through directly.
Yes.
So there's like a gap where the marble can jump over the
Yeah.
gap, but the electrons cannot go
Yeah.
through. Yeah.
Exactly. So which means so it's porous enough that lithiums can move,
Mm-hmm.
that ions can move,
Mm-hmm.
but the electrons get stuck. They do not move because there is no connection,
Mm-hmm.
right? And this happens on the first charging in the factory.
Okay. Mm-hmm.
right?
Mm-hmm.
And this is very important for it to work. But this is a double-edged sword.
Yeah, of course. How do you control so that it happens the right amount the first time, and then it doesn't keep happening? You want just the right amount of crust.
Yeah.
Yeah.
So it does three things. It stabilizes the electrolyte,
Mm-hmm.
right? It insulates electrons
Yeah.
while letting ions go through.
So the last two we just talked about. What do you mean by stabilizing the electrolyte?
If the electrolyte is not in contact with anode,
Mm-hmm.
with graphite, is
Mm-hmm.
not going to react.
Ah, okay. Okay, so you build up the crust so that electrons cannot go through
Yeah.
and lithium can go through, and also to make sure that the electrolyte and the anode don't react anymore. So
Yeah.
they naturally would react, but if you make them react a bit at the beginning, then they become insulated. Okay, understood. Mm-hmm.
So there is an optimal thickness to this solid level layer,
Mm-hmm.
right? Which they call it SEI, solid electrolyte interface.
Yeah.
That there's an optimal thickness.
Mm-hmm.
If it's too thick,
Mm-hmm.
then ions get stuck in the middle. So
Okay.
they
So. Mm-hmm.
that is the marble. If you have a net in the middle and the net becomes thicker and thicker,
Yeah.
they give their energy on the way down to that and
So
turn
there's
to
like,
heat.
yeah, this net or the crust, it causes some drag
Yeah,
on the marble, so it slows down
yeah,
when it goes through the
yeah.
through the net.
And this is where it comes like why we need to be able to study
Mm-hmm.
these surface characterizations are why so important
Yes.
to study how this grows,
Yes.
and you need to be able to do this electrochemistry and do this to see how this grows and how is the structure of it.
Yeah. So this is the interesting part, at least to me. This is what I really wanted to talk about today, because this is closer to what we do every day. Uh, we help all these companies that make this very high-end, very precise instrumentation to look at things like this, like surfaces on this crust. So how would that be done? Like if we want to improve the durability of batteries, uh, what what do we need to look for in that? Uh, you know.
Because let's continue. I think
Yes.
let's continue on the other thing. This is one of the
Okay.
things.
Okay.
All
Yeah, okay.
right.
So this is one factor
Yes.
that degrades batteries over time, but
Yes.
there's more. Okay.
Yes.
Okay. I didn't know.
So as you charge and discharge, this gets thicker and thicker,
Yep.
right?
Mm-hmm.
Because there is some residual electron that moves and such, and there is some resistivity and such, and then there is growing,
Okay.
right?
Mm-hmm.
So the other one is called lithium plating,
Mm-hmm.
right? Is we were talking about on the graphite,
Yeah.
it might be that we can elect instead of um, ions going inside the graphite between the layers
Mm-hmm.
and getting their electron back,
Mm-hmm.
might get it on the surface of graphite.
Okay. I see.
So essentially, they form metal on the surface of anode.
Okay. So some lithium is too greedy. It stuck to the graphite too early, and it doesn't let others through. Huh?
Yes, and the thing is that there are multiple things. Like now, it makes sense a lot of things.
Mm-hmm.
This happens on three factors:
Mm-hmm.
low temperature charging.
Uh-huh.
If you charge when the battery is too cold,
Mm-hmm.
then you see that these layers are too packed.
Okay.
So then lithium cannot easily go inside.
It has a harder time going inside, so it stuck to the surface,
Yes.
and then slowly it lets less and less lithium in.
Yeah, because it just essentially coats the surface.
Yeah, because so then even if you charge it again in a high temperature, still you have the plaque of.
Yes. And there's two sides. Is blocks the other lithium ions.
Yeah.
The other one removes lithium ions from the whole system. So there are less marbles
Ah,
because it's not a reversible factor anymore.
so they get stuck in there. So the marbles you had to play with, you have less and less because they
Yes.
are stuck on the. Okay, okay, okay.
So there are less marbles in the game.
So this is why, like, I kept hearing in the last year a lot, all these concerns. Now that electric vehicles are becoming more prevalent, there were all these concerns that they didn't work very well in like northern countries, and actually they are used way more in the Nordics and such, and people are quite concerned. So it's good
Yeah.
to know that's
The
why.
thing is that like also like I watch a lot of YouTube videos about cars and such.
Mm-hmm.
When they charge like in Teslas,
Mm-hmm.
when you want to charge and you say that you want to charge, it starts a preheating cycle
Ah,
on the battery.
okay, okay.
So put it at the optimal temperature so it can be charged.
Okay, okay.
So the second way that this can happen is
Mm-hmm.
if you charge it too fast, rapid
Uh-huh.
charging. Now you see like all the phones and such, they have this 100 watts, and the cars they say 15 minutes from 0 to 80% charge and such
Mm-hmm.
means, but it creates plating.
How
Why?
many minutes did you say?
15 minutes 0 to 80% sometimes
That's very
because
good.
they're just jammed.
I
They,
didn't know that it got that good. Like that's like as fast as a phone now, like charging a car. That's amazing. Okay.
yes, but like in 1 year of you doing it, like you just lose
Okay.
20% of the,
Okay. Okay.
like you know what I mean?
Okay.
Is kind of so if you charge it high too quickly,
Mhm.
what happens? Those
Mhm.
more so uh, lithium ions go there. They don't have enough time to penetrate into the layer,
Oh, okay.
and they get the charge.
So it's too rushed. Like,
Yes,
okay, let's get stuck and like, yeah, they don't have the patience to go in.
and the other one is overcharging.
Mhm.
Overcharging is also very cool because this happens. So overcharging means that the elect. So you remember last time said every six rings of graphite, one lithium ion can sit
Mhm.
in.
Mhm.
So if it's packed,
Mhm.
so the other ones gonna
Stay on the surface.
stay on the surface and plate create a coating on the surface.
Okay. 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 I see. I see. So it's so interesting that all of these totally different factors they cause the same effect. So the lithium plating is why batteries get less efficient, but it can happen because it's too cold, so the layers are too tight. It can happen because you charge it too fast and they stay on the surface, or it can happen because all the parking spots are full, so they stay on the surface.
Yeah.
Okay, okay, that's quite cool.
So again, here you see that why again a lot of things are important.
Mm-hmm.
How to control and study this.
Mm-hmm.
And there is some issues that it can happen. It's not only capacity that it reduces,
Mm-hmm.
but also creates safety risks
Okay.
because these are essentially crystallizing lithium, and it's not just a surface plate, it's a jacket structure
Okay. Okay.
that penetrates in the membrane in the middle and might make a short.
Oh, I see. So it's okay. So it's not like a smooth plating. It's
Yeah.
like a crystal, like a jagged crystal, and that affects the crust we were talking about before, the net that prevents
Yeah,
the
and also
electrons from going through.
the membrane that separates the cathode and anode because they
Okay,
are
so
separate from each other. There's
okay,
a
so
net.
there are these like spikes that can break through the membrane, and then it means that electrons can go through,
Yeah,
and that's a short then.
yeah,
So if electrons start going through the middle of the battery, yeah, then it's bad. Then it
yeah.
explodes. Huh? Okay.
So here again, if you can measure, study this first of all, how this grows, and the topography of the surface,
Mm-hmm.
how it changes,
Mm-hmm.
it gives you a lot of information.
Mhm.
If
Mhm.
you can see three-dimensional
Mhm.
how these crystallines are forming
Mhm.
on top,
Mhm.
and also you can do this in a microscopic layer level.
Mhm.
I mean, you need to just essentially do that. By the way, when I was thinking of this, for me was such a magic that this actually can work.
I know, I know. I was thinking about that because, like, a few episodes ago, we were talking about semiconductors, and that's all like solid state,
Yeah.
like it doesn't change that much. But thinking like inside our batteries, like it looks so tidy from the outside, but inside it's all this mess of different molecules and crystals, and like things grow and shrink, and the crust builds up, and yeah, it's it's hard to control that in a tidy way. It's very organic. It sounds like.
Yeah. 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 So, for example, the other one,
Hmm.
so we covered this SEI, which is
The solid
electrolyte.
electrolyte interface. So the like
Yeah.
net, the crust. Yeah.
We covered the plating,
Mm-hmm.
then cathode degradation.
Okay, so there's more. Okay.
Yes. So there's so many ways that this thing can go wrong.
Okay, okay, okay.
Right?
Let's see. Yes. Okay. Mm-hmm.
So, we said like this cathode, which is cobalt with oxide,
Yeah.
cobalt oxide. These these can go in and out, like the lithium ions can go in and out.
Yep.
After a while, starts degrading.
Okay. Mm-hmm. So is it again like a plating in front, or is
No,
it
it's
different?
essentially structural changes because you are literally put a stress every time that you pull a
Okay, so
lithium
it's
out
like
of it.
like what comes to my mind is like a snapping like plastic. I don't know when you, I don't know, in your shampoo bottle you have this plastic thing that snaps to open and close, and if you use it too much it degrades, and then it doesn't stay
Yeah,
closed. Is it like that, like it changes the
I
structure
don't know.
inside?
This is another thing that needs to be studied. Like
Yes,
that's
yes.
where. So, but like, think of it like if you're pulling between layers a marble out
Yeah,
and
yeah,
push
yeah,
it in,
yeah,
push
yeah,
it out, pull
yeah.
it. So after a while, it creates a stress into the whole structure,
Mm-hmm, mm-hmm.
and this structure changes, it contracts and expands if lithium ions are in or not.
Mm-hmm.
As this happens, it breathes again,
Okay, okay.
and it kind of creates a stress,
Mm-hmm,
and it breaks after a while.
mm-hmm.
Then the other one is chemically on the surface starts as we had electrolyte with anode,
Yeah,
also electrolyte with cathode can start reacting,
yeah, yeah,
right?
yeah.
So again, you can have a film on top of that, and this again,
That's Yeah, like the electrolyte is such a mess, like a mix of things. Huh? Like you can have so many different reactions and build up different, craft in there. Okay, so the electrolyte also reacts with the cathode.
yes. So essentially, the cobalt
Yeah.
can get dissolved in the electrolyte.
Oh, okay. So it's different now. So you are losing cobalt into the solution, like it's leaking out and
Yes.
Okay, okay, I see.
Because one of the good things about cobalt oxide bond
Yeah.
is that they are very strong. It's very strong.
Right.
But if you put a lot of uh, like voltage on it to
Right.
rapid charge it,
Mm-hmm.
you can dissolve cobalt because cobalt is also negative, positive.
Ah,
It's
okay.
like you're pooling lithiums, which is positive,
Yeah, yeah, yeah.
but cobalt is positive 3
Okay.
almost
Mm-hmm.
because like oxygen is such a hungry
Okay.
like electron lover
Mm-hmm. Mm-hmm.
that pulls all the electrons on itself,
Right.
and cobalt is positive 3,
So
and
the
it gets pulled out.
so the oxygen is quite close to the cobalt, so it's holding it in. But if you pull it too far, They go
Yeah,
off. Okay, okay. So I imagine that also affects the structure.
yeah, and this is also against charging and if you overcharge. Because imagine if there is no ions in the structure,
Yeah, so
there
it's
is not.
empty. The layers are
So
quite
what is
close.
next going? The cobalt.
Okay, okay. So if you are pulling and there's no lithium left, you
Yeah.
start pulling cobalt, huh?
Yes.
Okay, okay. Okay. Mm-hmm. Mm-hmm.
So the other one was film formation.
Mm-hmm. So is this when again the electrolyte reacts with the cathode and builds up a crust, or is it something different?
So it's electrolyte reacts with again.
Electrolyte reacts with the cathode.
Yes.
Yes, yes, yes. Mm-hmm.
The other one is oxygen release. You see that it
Okay.
bulges, like so if you are in a high state of charge, when
Uh-huh.
it's fully charged,
Uh-huh.
the oxygen,
So when it's fully charged,
if you're moving cobalt, the oxygen's less, it becomes a gas.
okay, yes, yes. So when it's fully charged, the cathode is empty. So then there's no more lithium left. So you start taking cobalt out. There's extra oxygens, which yeah, go up. So do they get released? Do they
So
get
two
mixed
things
into the
happens.
electrolyte?
That's cool.
Okay.
Oxygen is a oxygen oxidizes,
Okay. Yes. Yes.
right? And loves electron.
Okay. Yes.
And
Yes.
there are other things in the electrolyte. There
Okay.
are other positive
So
ions.
they get like you build up rust in the
Yeah.
electrolyte.
So it becomes a like bulging,
Oh,
and also so some of it goes as gas, some of it goes to the
I
electrolyte.
see. So okay. So if it becomes gas, then yeah, the whole battery starts inflating.
Yeah. That's
Do the batteries have some release for that?
no, you need to avoid this. They are like that's why charge management, the big part of the thing,
Mm-hmm.
like the your battery and the charger is a charge management. It's
Okay.
not just that you put a two what do you call two wires at the battery and charge them.
So they have like a chip or something that controls.
How much the state of charge is,
Yeah. So
how
so
fast
you
is
don't
charging.
charge it too much, too fast. Okay. Yeah. Yeah.
So then, how would you avoid, for example, this anode, sorry, cathode degradation, because that's a very expensive part of.
Well, I mean, we discussed it a bit last time. Like, you can always switch out the materials that have different properties, different electrolyte that doesn't react as much with the cathode, different cathode that is more stable. Yeah, the combination of both, and make sure that. Well, you said already that the cobalt is very tightly connected to the oxygen, so it doesn't get off easily. So more of that. So a material that where the metal is even more tightly connected. But yeah, I don't know. What are the solutions that are being explored right now?
So there are coating on the cathode,
Okay,
right, to remove the connection. So it's again another porous coating that allows lithium go.
okay. So you put another filter, another net in
Yeah.
front of the cathode,
Yes. And
so
you see,
that
all of these have a payoff. Like
yes,
they're
yes, of
like a
course,
cost.
because all of these they slow down the marbles, huh?
Yes.
So it's a bit more stable, but yeah, you have less energy. Mhm.
Yes. You don't let it charge as fast. You reduce charge density and all of
Yeah,
this.
it's very hard. Like the battery manufacturers, they have always this temptation to, charge it faster, charge it more, but you need to maintain this balance so that yeah, it doesn't get degraded. Okay, that's very interesting.
And the other one is um, doping.
Mm-hmm.
So essentially, they put instead of so they put it aluminum, uh, magnesium, titanium.
Mm-hmm.
They dope it with that
Into the structure.
into
Mm-hmm.
the structure to create stability.
So what does that accomplish? It means that. does it mean that the cobalt is held tighter, or that when you put, like, take lithium in and out, that the crystal structure stays stable? I guess it's a combination. Yeah?
To be honest, I don't know.
Mm-hmm.
I think here is partially is the structural stability,
Mm-hmm.
right? So you create, so you switch cathode, like a cobalt with titanium or aluminum,
Mm-hmm. Some of them.
some of them.
Mm-hmm.
So you have uh, differences like in two different, essentially two different lattices.
Mm-hmm. So the image that comes to my mind is like reinforced concrete.
Yes,
Like
yes,
you put some wires of aluminum or titanium in the middle of the
yeah,
cathode so that it stays stable. Huh?
yes. But
Yes.
in terms of atoms, right?
Yes, 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 of course. Yeah. Mm-hmm.
So, um, so the formula of electrolyte is very important.
Mm-hmm.
Again,
Yeah, because it sounds like it's so complex. Huh? You have
yes,
all these kind of salts and polymers in it, and it's so hard to avoid it reacting with stuff.
yes,
Mm-hmm.
and then temperature and voltage management,
Mm-hmm. Mm-hmm.
because the temperature is, again, if it's too low,
Yeah.
it degrades. It does the plating, lithium plating on the
Mm-hmm.
anode.
Mm-hmm.
If
Yes.
it's too warm, degrades the cathode and
Oh,
electrolyte.
I see. Okay, so the cathode one is if it's too warm. Okay,
Yes,
so if it's okay when it's warm. Okay, I see. I see. So when it's cold, the layers of the anode are too tight, so the lithium stays on the surface and it builds up a crust. But if it's too hot, the layers in the cathode are too loose, so the cobalt goes out.
yes.
Okay, okay. is this is this a real challenge? Like, I imagine the charge control and the temperature control.
Change temperature control is one of the hardest part of making
Why
electric
is it
cars.
hard? I would
Because
think that this is something that is solved, that is outside of the battery.
yes, but that needs energy.
Oh, okay. So if you spend too much energy in, okay, cooling it or heating it up, then
And the
it's
thing is
worthless.
that, like,
Okay.
the cars, like electric cars, they do not have a source of heat.
Okay, okay.
So if you want to make heat, either you need to make it based on resistance, like, like filaments,
Yeah, yeah, yeah. Like
or heat pumps,
mm-hmm.
right?
Yeah.
Which means that you need to spend energy to keep it in a energy range,
Yeah. And the filaments degrade as well.
temperature range. But the thing is
And
that
the
essentially it becomes a losing battle at some point
yeah,
if it's too cold.
yeah.
So first of all, the battery does not operate very well,
Mm-hmm.
right?
Yeah.
But then you spend that battery, that energy, to bring it to a temperature.
Mm-hmm. 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 Okay, okay. I see. I see. Mm-hmm.
So this is where essentially why we need all these devices. Let me see, bring it here.
Oh.
Like, for the guys and girls that listen to this, if there is any of you,
It's fine. In the video, you couldn't see it either. It's like a huge mess of arrows and tables.
that is why when I made the lab, designed the lab of future,
Yes.
and my what do you call it, where I loved to build if I had very good access to budget
Mm-hmm.
to make the dream lab,
Mm-hmm.
there are so many uh, material, like, labs that we need. Let's go through these labs and see.
Yeah.
So there is material synthesis and characterization lab.
Mm-hmm.
Now you know why you need to do synthesizing the material, like for electrolyte.
Yeah. You need to make all these crystals and all these mixes for the electrolyte, and then you need to measure their properties.
Yes.
So, what kind of measurements do you do on these materials?
So first, you need to know form what chemical reactions, or what chemicals are forming on the cathode and anode surfaces.
Okay, so the composition of that crust, like what is
Yes.
it? What?
chemicals are
molecules
there,
are in there.
molecules,
Yeah.
and what is bonded to what,
Yeah. Yeah.
or what
Okay.
is it. So that you need to have a spectroscopy techniques.
Mm-hmm. Mm-hmm.
Spectroscopy is spectrum. You need to come. So you need to figure out essentially, uh, as you would have a prism, then you would have a light, and you would distribute it the light, and you figure out what lights there is,
Yeah.
right? You can from that get the information of what was the light source,
Yeah. Mm-hmm.
right? So you have a spectroscopy techniques that gives the information about the built elemental elements that they are there,
Yeah. The
different
atoms. Yeah.
atoms
Mm-hmm.
or ions.
Mm-hmm.
The other one, what bonds they have formed.
Right. So yes, the molecules also have different
Yes,
signatures.
yes, because it's like essentially like there are two marbles that are in a with a like to extremely ridiculously like make it simplified, two marbles with a spring attached to each other,
Yeah. Yeah. Yeah.
and this have they jiggle with a
Mm-hmm.
specific frequency.
Oh yes, they resonate. This is when I was learning about drama and
Yes.
such. Yes, so you flash a light on the material, and based on how it wiggles, you know what
So reflects
molecules
in
are
a
there.
different light
Yeah, yeah, yeah.
pattern. So
Mm-hmm,
you need to do that, but then
mm-hmm,
you need to be able to do it in a very small, what do you call it, field of view.
mm-hmm.
So because it's not a homogeneous material like on the surfaces,
Okay.
you need to be knowing in that small area
Mm-hmm.
what is the build.
So
So you need,
high resolution because it changes over the
yes,
surface.
so you need to be able to combine microscopy techniques
Okay.
with the spectroscopy techniques.
Okay, so one is again looking at the materials in that area, the molecules and atoms in that area, and microscopy would be looking at it.
Yes, resolution, like to magnify it.
Yes, yes. So you literally take a picture of that
Yeah,
small pixel of the material.
yes, and there are so many different ways that are there.
Hmm.
Then electrode fabrication lab.
Let me
Yeah.
stop you. So, what are just mention the names? Like, what are the different things that can measure the composition of the material and the structure of the material?
Okay. So structural characterization.
Mm-hmm.
So you have in this lab, that which is like the lab name was material synthesis and characterization lab.
Mm-hmm.
In this lab, you have to have structural characterization.
Yep.
So you need to know what is the structure. What I mean by structure is not the molecule,
Yeah.
is the crystal structure.
Yeah. Is it for the surface or is
No,
it?
this is in the whole, like you analyze, like for example, think of it as what do you call, like for example, if you have a sugar crystals, when
Yeah.
you grew sugar crystal in
Yeah.
like a
Yeah.
I know primary school,
Yeah.
right? Science. So you needed to. So the thing is that these are like crystals are repeated patterns of atoms,
Yeah.
right?
Yeah. And like a
And
grid
right,
complex.
yes,
Yeah.
and you use them, like I don't know if you remember or heard about Young experiment,
I've heard.
like a
Is
double
this?
slit
Yes.
experiment
This
that
is
you put a
the
light.
X-ray crystallography.
This is XRD. No, no, the Young is a different thing. For
Okay.
example, if you have a source of light
Yeah.
and you have two very narrow slots,
Yeah.
and this source of light needs to be very thin and not like what do you call it, comes very from a point object, point source,
Yeah. 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 Like they talk about. Yeah. This
coherence
the
and
double
such,
slit experiment where
right?
you. Yeah. Sometimes it's a single photon that
Yes,
they
but
pass through.
the form, the like you see that, like for example, it makes a pattern,
Yeah.
and the pattern, it depends on how far these slots they are.
Mm-hmm. Mm-hmm.
So think of crystals.
Mm-hmm.
Now you don't have two slots. All of these are reflection points, these
Oh.
atoms, that is repeating itself in three
Okay.
dimensions.
Okay. Okay.
So now if you shine a light to it,
Okay.
it makes a structure.
Okay. So Even with just two slits,
Yeah.
the end result, the refraction image is quite complex. Like,
But the distance between those
yeah, 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 yeah.
is a function of distance between these two slits.
Mm-hmm, mm-hmm,
Imagine now adding more of them
mm-hmm.
and shining a light.
Okay. Mm-hmm,
Now, think of this. You have um,
mm-hmm.
in the crystal, you
Yeah,
have many of these dots that is repeating.
yeah,
Imagine that they are that where they block the light, and between them, the light goes through.
yeah, yeah, yeah,
So the pattern that is scattered
yeah.
can tell you how the crystal structure is.
Mm-hmm, mm-hmm, mm-hmm. So you shine a light through it, and
Yeah.
then you take a picture of what comes out.
Yes,
Okay.
X-ray.
Mm-hmm.
And this is how they realize the double helix of DNA.
Yes, 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 yes,
Rosalind.
yes, yes.
Yeah.
This is the yeah, yeah, yeah. Yeah, my father did a bit of like polymer
Yeah.
crystallography. Yeah, yeah, nice.
So you need X-ray diffraction.
Yeah,
So all the long way
that's
of
the
making
diffraction part. Okay,
so
yes.
characterization,
Let's just mention the names so that they are
right?
loosely familiar to people.
So then you have a single crystal diffraction
Yeah, that sounds
or like a
similar.
powder diffraction.
Mm-hmm.
Then you have a scanning electron microscope.
Mm-hmm. Mm-hmm.
This is instead of light using electron.
Yeah, so you have a beam like of electrons that you shine on the material.
And then
You just bombard the
yeah,
material with electrons and measure how they bounce out.
yes.
Okay.
Then transmission electron microscopy, TEM.
Yeah,
So instead of looking at the scattered electron, you look at the
the ones that
one
pass
that
through.
pass through.
And this can also image the structure, the 3D structure of the material. It's not just the surface. So
Yes,
electrons can go through the material.
yes,
And
yes.
Mhm,
There is a bit of a difference here, and like how what information you can get.
mhm, mhm.
Then there is cryogenic, so temperature
Yeah,
again,
sure.
temperature cryogenic,
Yeah.
right? And then ion beam and such. This is
So ion beam is like the electron beam,
yes,
but instead of electrons, you have
yes, ion,
uh, like lithium ions that we were saying before.
yes,
I
but
don't
this is
think they
ion.
use lithium, but yeah.
And then X-ray microscopy. Then you have chemical characterization tools that you need to
So
have.
this is a spectroscopy.
This is spectroscopy. The other one was a structure.
Yeah,
This is chemistry,
yeah, yeah, yeah.
right? Then
So counting how much of each element is
yes,
in there.
then energy dispersive X-ray spectroscopy (EDX).
Mm-hmm.
So the cool thing is that because a lot of these things you can do it in the same tool.
Uh-huh.
Because if you have an X-ray,
Mm-hmm.
you can look at the pattern, but also dispersion of the energy. How much energy was given and how much energy.
It was lost. Okay.
Yeah,
Uh-huh.
it gives you information about the chemistry.
Because yeah, like when I was looking into this, you both measure how much goes through the material, how much bounces out of the material, how much it resonates with the material, how much the material diffracts.
Yeah,
But it's all just shining a light on it and measuring
yeah,
different ways the light comes out of it. And
yeah.
when I say light, it's X-ray, but X-ray is still light. It's just a
Yes.
different frequency. Yeah.
The other one is like for example, X-ray and other types of X-ray, photo electron, FTIR, Fourier transform, spectroscopy,
So Fourier
Raman,
transform, it will be on the frequency. So
yeah,
okay.
Raman spectroscopy, NMR, nuclear magnetic resonance spectroscopy,
Uh huh.
which means that now look at the nuclear, like the nuclei
Yeah.
and the spin of them,
So instead of
and see what
shining,
build of what materials they are.
so instead of shining an X-ray on it and having the vibrate, this is
RF,
like
radio frequency, radio.
magnetic field, and you have them resonate
Yeah, so you
and
have a
vibrate.
magnetic field to put all of them in align them,
Uh huh. Yeah.
and then you make an RF radio frequency
Right.
that flips the spins,
Okay. Okay.
and then they come back and they make another radio frequency back.
Okay. So okay, you flip them, and then when they come back, you
It's
measure
the
what
same
happens. Okay.
concept, but in a different frequency range.
Okay. Okay.
These are so cool.
But that's why you can have a lot of this in the same instrument, because it's mostly about bombarding the material with stuff,
Yes.
either light or electrons or ions, and then taking a picture of
Yeah,
what
but
comes
like
out.
in these NMRs are 2 million euros or
Yeah,
something,
yeah, yeah,
right?
yeah, yeah.
You need a
It's
like a you need have like MRI is
Yeah,
the
yeah,
same.
yeah, 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 yeah. Like the way we are explaining it is like the ramp of the battery, but then we saw how complex it is. You know, every all this is a black hole
Yes,
complexity, and it needs to be super precise, which is a lot of the complexity.
yes.
Like if you could make a basic one that is not very good, but yeah, you need a lot to yeah.
And then you have to have mass spectrometry techniques,
Mm-hmm, mm-hmm.
right?
Yes. So this yeah, so it's not spectroscopy, it's spectrometry,
Yes.
mass spectrometry. And I remember this was yeah, mostly about so you take small particles of the material,
Yeah.
you throw them in a magnetic field, and you see how they curve in the
Yeah.
magnetic field.
If they are ions.
Yes, so you need to yeah, they need to be ions. So they curve in the magnetic field, and based on where they end up and the at the
Radius of the curve.
yes, yes. So you have again some
You figure
sensors.
out what is the mass of them.
Yeah, yeah, yeah.
So
Ah, okay, yes. So how much they weigh?
yes.
Essentially, yeah, yeah.
So because each atom has a unique, so that you have a atomic number
Mm-hmm.
and number of neutron.
Mm-hmm.
So you can see, given their charge,
Mm-hmm.
so essentially where how much they deflected,
Yeah.
you can figure out what atom they are,
I imagine like if you have a ramp and you throw a
what elements
marble,
it is.
you throw a marble like laterally,
Yeah,
based on how soon it goes down, you
yeah.
can see, how much it weighs. Yeah, yeah.
And then you have to have thermoanalysis tools
Okay.
like
Thermogravimetric.
gravimetric
So how
analysis.
much
How much?
the weight changes based on the
No,
temperature?
it's essentially how much energy they can, thermal energy they can get and such.
Mm-hmm. So how much it can hold,
Yes,
so how quickly? Okay.
calor calorimetry
Mm-hmm.
and macrocalorimetry. I don't know these techniques at all.
Mm-hmm. Mm-hmm.
So then you have porosity analysis, surface analysis,
Mm-hmm.
right? You have different techniques of surface
How
analysis.
rugged it is, how much it lets, ions
Yes,
through.
and how topography of the surfaces, AFMs, they are here, use atomic force
Yeah, it's
microscopy,
like
use.
a map, like a satellite, elevation map of the
Yes.
material. Yeah.
Then you have elemental and isotopic material.
Gas absorption. Okay, yeah.
And this is time of flight ion mass spectrometry, TOF SIMS.
Mm-hmm.
And then uh, dynamic and electrochemical analysis,
Mm-hmm.
defect analysis, and the other advanced imaging and vacuum techniques.
Yeah, good. I just wanted to float all these names, so that people at least hear them once, and then maybe if they hear them again, they can associate.
Yes.
But it's very hard to go deep into this in this time.
Yeah, so such a complex, and this is not even like a few of them, and then you have different flavors of this,
Yeah.
different combination of them, different optimization for different things,
Mm-hmm.
and each of these labs or each of these equipments are long and big companies behind them developing them, mostly coming from the universities and spin-offs of the universities,
Yeah.
and becoming big and being bought by these big enterprises.
Mm-hmm.
And then that's how the ecosystem behind this is, that is mostly unknown to the uh, wider public.
Yeah.
For example, a company like Thermo Fisher has $36 billion revenue a year,
Yeah.
and that's huge.
Yeah. And
And
some of them, as you say, they make themselves, but a lot of them, it was PhDs that they did their PhD on a new improvement of the instrument, and then they try to make a small startup out of it, and then the big company bought it and they help
yeah,
sell. Mm-hmm.
and it's a whole ecosystem there,
Yeah.
that a lot of cool technologies are being developed
Mm-hmm.
and used,
Mm-hmm.
and nobody knows what it goes to small cell phone batteries.
Yeah. 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 Yeah.
You know, all of these uncool sciences,
Yes.
which I'm happy now we're at the time that actually uh,
Yeah.
being a
People
scientist
are
becoming
trying to
cool,
notice. Yes. Yes. Mm-hmm.
right? But then that is where essentially I can think of, and I can be happy that at least these things are becoming cool again.
That's a nice bow on top. Again, we go back to deep tech, huh?
Yes.
Like making this science cool. Like the boring stuff, now it's becoming
Yeah,
cool.
but the thing is that what I'm sad about it is that most of it geopolitics become leads to that, not
Mm-hmm.
the challenges that we have as a humanity as a whole.
Mm-hmm.
Like COVID, the good thing about it was that like everyone was collaborating to an
Mm-hmm.
extent.
Mm-hmm. Mm-hmm.
I'm not sure if how it was, but like
Yeah.
if you think of it, because there was a kind of common enemy.
Yeah. But to some extent also, like, people wanted to be first because, they could sell a lot of
Yeah.
vaccines. So
It,
yeah.
still there is a, which is a healthy competition.
Yes, yes. That actually probably helped. Yeah.
Yeah. But in a sense that being the motive of doing that because someone else is cutting our gas or something is
Yeah.
kind of interhuman competition
Yeah. Yeah. Yeah.
versus intra,
Yeah.
like when we have a problem. But that's cool.
Yes.
But yeah, that was it. I hope that you enjoyed it as much as we did.
Yes. Thank you, Mary, again. Like
Thank
another
you.
one where, you teach me, but it's very good. I
Yes,
really
but
enjoy
it's
it.
cool. But yeah, let's see if we can continue this conversation in other parts of the battery, other things, or we move to another topic next.
We were talking about AI earlier. We know a
Yeah,
lot about that as well. We haven't talked about it, but
but
it's our
yeah,
bread and
I
butter
think
as
what
well.
we know it's, yeah, we use it on the daily basis, but
Hmm.
yeah, AI is my teacher now.
Yes, yes.
Very good.
Yes.
Thank you, John.
Thank you.
Thank you, everyone.
All right.
Have a great rest of the day,
Yes.
guys.
Bye
Bye.
bye.